Archie? I guess I'm not good enough. Where are my kisses? Oh, but you can see Annie, so that's exciting. Cool. Well, anyway, let's dive in because I need to finish recording this set of lectures before I get my COVID vaccine on Friday because I will probably not be useful. So, yeah, let's do that. Hi again. So today we're going to talk about response functions. Item response functions. Right. And the equations that go into them. So I'm going to work my way backwards. So we're going to start with the 4-parameter model, and then I'll show you which piece and kind of take it away as we go. So they'll get simpler and simpler. So the 4-parameter logistic model is mapping the probability of endorsement of an item as a function of theta, their trait level, B, the item difficulty, and that's determined by the location of the item response function. A, which is the item's discrimination, which is determined by the steepness of the item response function. C, which is the lower asymptotic parameter, and D, which is the upper asymptotic parameter. So P is a function. That's what's happening. And then if we go across to the other side of the equal sign, it tells us how all those pieces are related. The P of X given blah, blah, blah. That's just telling us all the inputs. Now, in order to model this, here are the pieces. So we add the lower asymptotic parameter plus the difference between the upper asymptote and the lower asymptote. And that difference is multiplied by a log of e to the a, which is a function of theta minus b. I'm not going to expect you to be able to crawl deeply in here, but the idea here is that there is a mathematical function that maps out all of these parameters. Where the Archie, what are you doing? Ah! Okay, let's try this again. Now I just need to cut and start. So the 3-parameter logistical model is very similar to the 4-parameter model. But instead of having the upper asymptote, so that's the D parameter, we have replaced it with a 1, which then turns this entire model into a 3PL model. And in this model, the individuals with low trait levels have a non-zero probability of endorsing the item, but those on high trait levels effectively have a near perfect probability of endorsing the item. 2PL. So here we've cut out the lower asymptote entirely. So instead of having that C parameter plus this equation here with the e to the a power, etc., now we only have that logistical model. So now the lower asymptotic parameter is constrained to 0. So in the 2PL model, IRFs vary both as a function of discrimination and their difficulty, i.e. their location parameters. So there are 3
pieces of information that we kind of, well, 4 technically. But anyway, in the 2PL model, we have 2 parameters, that's A and B, plus our theta, which is our estimated ability level. Or actually, it's our true ability level. Okay, now let's take a step even further back. So here we are down to just one parameter because the item discrimination has now been fixed to 1. It can be any other constant, but the end result is a 1PL model. And a 1PL model assumes that all scale items relate to the latent trait equally, and items only vary in order of how difficult they are. So that's the equivalent to having equal factor loadings on items. And it's also practically the equivalent of taking the average of the items. By treating each item as equally important. That's what an average does. It reweights them so they're equally valuable in the mean. Okay, so let's do a little quick detour. So mathematically, Roche models are identical to the most basic IRT model. So that's the 1PL model. However, there are some small but important differences. In the Roche model, the model is superior. Data which does not fit the model is discarded. Roche doesn't permit abilities to be estimated from extreme items or persons. And I mean, there are a couple other differences that I'm happy to talk about in office hours, but it's a more strict version. That as much as I instinctively want to say they're equivalent, they're not. IRT is much more flexible. All right, so test response curves. So a test response curve is the latent trait relative to the number of items. So effectively, we are just adding up item response functions so that we can see what the total score is. So the total estimated ability is a function of this test. And we can kind of get a sense of the relationship between the expected number of questions that you get correct versus the trait level. So on this test response curve, you can interpret it the exact same way as an item response curve, except it's the total, a cumulative effect. So here, someone at a trait level of 4, we can trace up to see where they hit the line, and we'd expect, on average, them to score about 18 items. And as we move our way down, we can see that someone who is average or typical in our sample would score approximately 5 items. Okay, cool. So I'm going to wrap up here because, well, I know that the previous video was pretty long. So cool. But now that we've wrapped up here, I'll see you in the next video.